Hello everybody, it's Tarun. Welcome to your 20th tutorial in the Signal System and Control course. In the last tutorial, I taught you the impulse train sampling and the basic sampling theorem. In this tutorial, I will start with reconstruction. Okay. So, what is actually reconstruction? It is the derivation of sampling theorem, or we can say that we are going to construct our signal x of t from the samples x of n t. Okay. And how we are going to do that? And we are going to do that by generating weighted impulse trains and subsequent ideal low pass filtering. So now let's start with the ideal reconstruction. Okay, for ideal reconstruction, this is the block diagram or the system diagram, where we are first creating our simple signal xp of t, and then we are passing it through low pass filter, then we are getting a reconstructed signal. So this is the characteristics of our ideal low pass filter. H of j omega is equal to t rectangular omega upon 2 omega c, and its Fourier transform representation, it was the Fourier transform representation in the frequency domain, and then its inverse Fourier will be h of t equals to omega c t upon pi sinc omega ct upon pi. Here you can use pi if you want, or you need not use pi if you are not comfortable with it. Okay, and this ideal low pass filter has cutoff frequency omega c, which lies between omega m and omega s minus omega m. Okay, so now let's talk in the first thing, the time domain. In the time domain, xrt will be xp of t convolution h of t, where h of t is the impulse response of the low pass filter. Okay, so this is the impulse response. So xrt will be this expression, okay, where you all know that the term in the square braces is xp of t, and this expression is h of t. And then after convolution, this expression will look like this. Okay, here what had happened, the omega ct upon pi has remained unchanged, similar to x of nt, and the sinc function has been convoluted with delta function, which resulted into this function. Okay, so just memorize these functions, or in some institutes also the exam conducted with these type of expressions are open book, or formula sheet is allowed in the examination. So depending on your institute, you can choose whatever way is easy for you. Okay, so but I'll suggest that you memorize these equations in the sampling unit, because these memorizations will help you solve the questions very easily. Okay, and this time domain interpretation of the reconstruction is called ideal band limited interpolation. Okay, and if omega c is equals to omega s by 2, okay, so this was our sinc function. Okay, and if we increase the value of n, the signal will vary, as you can see in the graph. So there are a few practical issues with this type of reconstruction. Okay, as you all know that ideal low pass filtering is impossible, which is there in the practical issues. And the second issue is that narrow large amplitude pulses are difficult to generate, which means that we are till now talking about the impulse trains, but to generate impulse trains with zero width, it is not possible. So there is practical issue there. Okay, so now let's move forward to the non-ideal practical reconstruction. Okay, it will contain two methods. The first one is zero order hold interpolation, and the second one is first order hold interpolation. So what does the value hold mean? It means that hold the value of x and t until the next sample. So this is the reconstructed signal, and it was our original signal, the signal represented in dotted line here. Okay, so what does it say? that wait for the signal till next sample occurs. So now let's see the reconstructed signal. Here the reconstructed signal XRT is the method is same. We are passing the sample signal through a low pass filter. Okay, but in the three cases, first one is the ideal band limited interpolation, second one zero order hold, and third one first order hold. The value of or the impulse response of the low pass filters will change. So in this case, the impulse response for the low pass filter is this function, rectangular function. Okay, and it is the zero order hold interpolation impulse 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 response is represented by h naught t, which is equals to rectangular t upon capital T minus 1 by 2. Okay, if I want to see it in the frequency domain, then first I will Fourier transform h naught of t, which will be h naught of j omega, which is equals to t sin omega t upon 2 pi e to the power minus j omega capital T by 2. Okay, which is the Fourier transform for the h naught of t function. Okay, and this is the model for the zero order hold impulse train reconstruction. Okay, it is similar to the ideal reconstruction, but the impulse response and the frequency response have changed of the low pass filter in this case. So in the frequency domain, so the spectrums of the reconstructed signal will be like this. Okay, with the help of multiplication property or the convolution property, you can see that the frequency domain reconstructed signal will be the multiplication of the impulse response, the frequency response of the ideal low pass filter, and the Fourier, the representation of sample signals in the frequency domain. Okay, which when you will solve will look like this. Okay, and I'll suggest that you just go through it thoroughly, so you will not get any problem. So this was our signal xp of j omega, these lobes, triangular lobes, and this signal is our sinc function. Okay, and when I pass it through the zero order hold interpolator, then after taking the modulus or plotting the magnitude spectra, it will look like this. Okay, so what are the effects of zero order hold interpolator? The first one is that the linear phase shift corresponding to a time delay of t by 2. Okay, and the portion between omega m minus omega and omega m gets some distorted, and there are some distorted and attenuated version of x of j omega. Okay, so we can reduce and or eliminate effects of distortion and aliasing by adding one more filter, which is continuous time compensation filter, or called anti-imaging filter, and its frequency response is this. So if I pass the signal through first zero order hold interpolator and then through anti-imaging filter, then I'll get my signal XRT, which will be very much equal to our original signal x of t. Okay, another non-ideal interpolation procedure, which is linear interpolation, first order hold interpolation. Okay, so the XRT, which is reconstructed signal, looks like this in this case, where the dotted signal represents the original signal xt of t, and the interpolation filter, first order interpolation filter, its impulse response has the following curve, and its transfer function or frequency response is this. Okay, so I'm not going to detail into this interpolation method, but I'm going to just tell you. Okay, so this was the first order hold interpolator, and as the second and higher order hold interpolator we go, the smoothness of the curve increases. So this is the comparison for interpolation transfer functions. Okay, the square wave you can see here is the ideal in the interpolation filter, and this one is the first order Holt interpolator, and this one is the second zero order Holt interpolator. So as you can see that as the order increase, the curve is trying to get smooth, so it will try to reach the ideality, but it will not reach ideality ever. Okay, so now we'll start with the next topic, which is the aliasing or effect of undersampling. So if the condition of sampling theorem, which is omega s should be greater than equals to 2 omega m, is not met, which is omega s is less than 2 omega m, then the spectrum of xt will not be replicated in xp of j omega. Okay, and the xt will not be recoverable by the low pass filtering. So now let's see it with the individual terms. So our sample signal in the frequency domain is like this, and the overlap in the curve of this function where omega s is less than 2 omega m will look like this, and this overlap is referred to as aliasing. So if I take the low pass filter where cutoff frequency omega c is equals to omega s by 2 for reconstruction, then the reconstructed signal will look like this, and but the XRT, which is the reconstructed signal, will not be equals to our original signal x of t, but the integer multiple or the scalar multiple when the independent variable t in the reconstructed signal and the original signal will be same. So these are the few observations or effects of aliasing. Okay, so now let's see one example. Critical sampling of sinusoid signal. Okay, critical sampling is Nyquist rate sampling where omega s is equals to 2 omega m. X of t is cos omega naught t plus 5. So we are sampling the signal at exactly twice the frequency of the sinusoid, where omega s is equals to 2 omega naught. Okay, and the frequency domain representation or the frequency domain expression of the signal x of t will be like this, which you can all find out as I have told you the Fourier transform for both the continuous and discrete time signals. Okay, so when I multiply the signal x of j omega or convolute it with the periodic impulse or impulse stream, then I'll get the sample signal with the expression like this, and the plot will look like this. Okay, and it is the plot of the original signal and it is the plot of our sampled signal. So if I am constructing it with ideal low pass filter whose cutoff frequency lies between omega s by 2 and omega s plus omega s by 2, and it is having gain t, and then the reconstructed signal in frequency domain will be like this, and in the time domain it will be like this expression. Okay, so obviously you can see that the signal x of t is equals to xr of t. Okay, but only if phi is equals to 2 pi n. Okay, and n belongs to integers. Otherwise xrt is not equals to x of t. So example, if phi equals to minus pi by 2, then xrt will be 0 because cos minus pi by 2 is 0. So x of t will be sine omega s t by 2 in that case, but xrt will be 0. So this proves the constraint which was there in phi, which must be equals to 2 pi n. So there is a note regarding the sampling theorem. Okay, the sampling theorem explicitly requires that sampling frequency must be greater than twice the highest frequency in the signal, rather than greater than or equal to twice the highest frequency. Okay, the subtle difference is important for signals whose spectra capture energy at omega equals to omega n, that is, whose spectra includes omega minus omega n. So if omega s equals to 2 omega m is chosen for such signals, then additional phase information is required for correct construction. As you can see in the above example, that if you would have taken omega s greater than 2 omega m case, then the constraint might not be required in the above example, but we talked about the critical sampling in the above example. That's why we required a constraint in the phase, okay, which was necessary for constructing the signal to its original very precisely. Okay, so now let's see the discrete time processing of continuous time. This is processing which we are going to do because the processing of discrete time signals is preferred as compared to continuous time signals. Okay, it is because the processing of continuous time signals is quite difficult to understand and to process, because the continuous time signals has no gap between the information, and in the discrete time signal you are having some samples, so you can divide them or treat them as packets, and you can treat one packet as one information and you can process it individually. Okay, so we'll decompose the continuous time system in cascade of 3 operations. Okay, first of all is x of x c of t, which is a continuous time signal, and we are converting it to discrete time, which will be x d of n, and then passing through discrete time system where we'll process the signal, we'll get our output y d of n, and then we'll again convert it to continuous time signal, which will be yc of t. Okay, so the continuous time input xc of t and output yc of t, and their corresponding discrete time signals xd of n and yd of n. So theoretical basis for conversion is the sampling theorem. Okay, continuous to discrete time conversion, sampling with sampling period t, and discrete to continuous time conversion is the reconstruction. Okay, so this is again the block diagram in another manner. Okay, digital systems are often represented as A to D and D to A, which are analog to digital and digital to analog converter respectively. So now let's see the sampling of discrete time signals. Okay, sampling mechanism can also be applied on the discrete time signals. Now let's see, the first thing is the impulse train sampling in the discrete time signal. I am having xp of n as my sample signal, okay, which will be equals to x of n if n is an integer multiple of n, where capital N is the sampling period, which belongs to natural numbers, and it is 0 otherwise. So a representation by means of discrete time impulse train, it will be p of n, it will be equals to summation k equals to minus infinite to infinite delta of n minus k capital N, and with Fourier transform and the sampling frequency omega s is equal to 2 pi by n, the Fourier transform of p of n will be this. So as similar to the sampling of continuous time signal, the diagram is similar. Okay, and the expression you can find out by multiplying x of n and p of n. So now let's illustrate the example, the sampling of discrete time signals. This was our original signal x of n, and it was our impulse train p of n. Okay, so when I multiply these two, I'll get the terms only at the integer multiple of capital N, as you can see here. Okay, so frequency domain you can see with the help of multiplication property that xp of n will be xp e to the power j omega, and it will be periodic convolution of x of n and p of n, okay, which will be in the frequency domain only. So case 1 for the discrete time sampling or the sampling where omega s is greater than 2 omega m, where no aliasing occurs. Okay, this was our frequency domain signal, original signal, and it is our impulse train in the frequency domain, and when I multiply these two, I'll get periodic sampled signal. Okay, if I pass it through low pass filter, then I'll get my original signal. Okay, and the case 2 is aliasing. where omega s is less than 2 omega m, and the curve will look like this because of overlapping. Okay, so that's all from my side in this tutorial, and we have ended unit 6. In the next unit I'll start with Laplace transform in the next tutorial. So thank you guys for watching. I'll see you in the next tutorial.